the hidden engine behind tornadoes. When most people picture a tornado, they think of the swirling funnel cloud tearing through the landscape. But behind that violent spin lies a hidden force, one that plays a key role in whether a tornado forms, strengthens, or dissipates. This force is called the rear flank downdraft, or RFD. It's one of the most fascinating and least understood parts of a supercell thunderstorm. The RFD is a powerful current of air that descends from high up in the storm and wraps around its backside. It's cool, dry, and invisible, yet it's often the trigger that causes tornadoes to spin up near the ground. In many ways, the RFD is the secret engine that drives the birth of tornadoes. Without it, most twisters simply wouldn't exist. How the RFD forms. Inside every supercell thunderstorm, intense updrafts pull warm, moist air upward while rain and hail fall through layers of drier air below. As that precipitation falls, it evaporates, cooling the air around it. Cooler air becomes denser and heavier, so it sinks rapidly, forming a downdraft. When this downdraft develops on the backside of the storm's rotating updraft, it becomes what meteorologists call the rear flank downdraft. When it slams into the ground, it spreads outward like a gust front, wrapping around the base of the storm and creating a sharp boundary between warm, humid inflow and cool, descending air. That collision zone becomes the perfect breeding ground for rotation near the surface, where tornadoes are born. The temperature balance that sparks tornadoes. One of the most crucial details about the RFD is temperature. If the air inside the RFD is too cold, it can actually choke the storm's updraft, killing any chance of a tornado forming. But if it's only slightly cooler than the surrounding air, it creates the ideal conditions for rotation. Studies show that when the RFD is about 3 to 6 degrees Celsius colder than the surrounding environment, the contrast in air density helps tighten and stretch the storm's rotation. In simple terms, the RFD gives the storm just enough push to start spinning faster, much like an ice skater pulling in their arms to spin more rapidly. This delicate temperature difference can decide whether a storm produces a weak funnel or a violent EF5 tornado. How the RFD helps create a tornado. As the RFD wraps around the storm's central updraft, called the mesocyclone, it forces air inward and upward. This process helps concentrate rotation at the surface, often leading to the visible funnel cloud we recognize as a tornado. At the same time, the RFD pushes warm, moist inflow air upward into the storm, feeding its energy and maintaining the circulation. Essentially, the RFD and updraft are partners in motion. One pulls upward, the other wraps around and tightens the spin. Without that balance, even the most powerful supercell might never produce a tornado. Recognizing the RFD in the field, storm chasers often rely on visual cues to identify the RFD. One of the most evident signs is a clear slot, a bright rain-free gap that forms near the base of a rotating wall cloud. This happens because the RFD's dry air is cutting through the storm's moist core, clearing out rain and creating a visible window into the tornado's potential birthplace. When a clear slot wraps around a wall cloud, it usually signals that the storm is organizing and may produce a tornado at any moment. At ground level, chasers might feel a sudden drop in temperature, shifting winds, or see debris and dust wrapping around the storm's backside. All evidence that the RFD is active. The RFD, creator and destroyer. The RFD has a dual personality. While it's often responsible for triggering tornado formation, it can just as easily destroy the very tornado it helped create. When the RFD becomes too strong or too cold, it overwhelms the storm's inflow, cutting off the warm, moist air feeding the tornado. When that happens, the tornado starts to weaken, its funnel narrowing and twisting before it eventually fades, a process storm chasers call the rope-out stage. In short, the RFD can act as both a midwife and a killer. The same downdraft that gives birth to a tornado can also smother it moments later. The science of RFD detection. Meteorologists have made significant strides in understanding the RFD thanks to Doppler radar and mobile research units such as Doppler on wheels. On radar scans, the RFD appears as a region of strong outbound winds, a burst of air moving away from the radar, located behind the main rotation. When you see green and red colors side by side on radar, indicating air moving toward and away from the radar simultaneously, That's often where the RFD is wrapping around the mesocyclone. Mobile radar units have even captured how bursts of descending air in the RFD align precisely with tornado touchdowns, proving how directly linked the two forces are. The visual impact of the RFD beyond radar. The RFD also shapes how a storm looks from the ground. As the downdraft descends, it can carve dramatic features into the supercell, such as the clear slot or the horseshoe-shaped cloud base wrapping around the funnel. When sunlight breaks through the RFD's dry slot, it sometimes illuminates the tornado itself, giving chasers that classic view of a dark funnel against a glowing sky. The visual drama of these storms, the color contrasts, the swirling dust, the light beams through the cloud gaps, owes much of its power to the RFD. Why the RFD still mystifies scientists. Even after decades of study, scientists still don't fully understand why some RFDs produce violent tornadoes while others don't. The interactions between air temperature, pressure, humidity, and storm motion are incredibly complex. Sometimes, two storms may look nearly identical on radar, yet only one produces a tornado. The difference often lies in subtle shifts within the RFD, a few degrees of temperature change, a slightly drier air mass, or a faster downward motion. Capturing those differences in real time remains a challenge, which is why researchers continue chasing storms to measure the RFD more accurately. The future of RFD research. A better understanding of the RFD could transform tornado forecasting. Suppose meteorologists can identify the temperature and wind structure of the RFD as a storm develops. In that case, they may be able to predict with much greater accuracy when and where a tornado will form. New high-resolution radar networks, drones, and machine learning models are already being used to analyze how RFDs evolve during severe storms. Each storm chased and recorded brings scientists closer to cracking the code behind tornado genesis. The ultimate goal is to give people more lead time and more lives saved by recognizing the RFD's fingerprints early. The RFD's role in tornado safety. Understanding the RFD isn't just for scientists and storm chasers. It's vital for public safety. When the RFD wraps around a storm, it often causes rapid wind shifts and sudden pressure drops, which can happen seconds before a tornado forms. Recognizing those signs can give spotters and meteorologists critical warning moments. By watching for the clear slot, changes in wind direction, or a sudden burst of dust and debris, chasers can identify when a tornado is imminent, even before radar confirms it. That's why modern tornado warnings often mention rotation tightening or RFD surging. They're clues that the storm is transitioning from dangerous to deadly. The hidden power of the RFD. In the end, the rear flank downdraft is one of nature's most mysterious balancing acts. It's both destructive and creative, the unseen hand that decides whether a storm becomes just another thunderhead or a catastrophic tornado. While we may not fully understand it yet, every storm study brings us closer to unveiling its secrets.